Welcome to ECE 3300 at the University of Utah. In lecture number 12, we're going to be talking about Smith charts. Before we start, please go to the class website and print out a few Smith charts to take notes on. The other reason you'll need some Smith charts is because the numbers are very tiny to be able to see them on this video, and you'll need a Smith chart in front of you. A Smith chart is very useful for two things. The first is calculation, particularly kind of back-of-the-envelope rough calculations. The second, and perhaps more important use of the Smith chart today, is that much of our measuring equipment in the RF region displays our results on a Smith chart, so it's important to understand what you see when you see values plotted on a Smith chart. A Smith chart is used to analyze a transmission line that is working in steady state. That means that the generator is sinusoidal. So our signal is sinusoidal, all the transients have died away, and now we are working in a steady state or continuous wave. Sometimes it's called continuous wave or CW. So it's a sinusoidal excitation with no transients. It has reached its steady state, and that's what we're going to be analyzing with the Smith chart. These are the things that we're going to be studying: how to plot or find the reflection coefficient in its real and imaginary or polar form, the transmission coefficient, the various impedances on the line, how to rotate or move distances toward the generator or toward the load, how to calculate the admittances on the line, the voltage standing wave ratios, and the location of the minima and maxima of the standing wave envelope. Let's first talk about the reflection coefficient. Remember that the reflection coefficient is related to the load impedance and the characteristic impedance of the line. The largest reflection coefficient we have will happen when we have an open circuit. In that case, ZL is equal to infinity, and the reflection coefficient will be 1. The smallest reflection coefficient will happen when we have a short circuit. In that case, the load is 0, and the reflection coefficient is -1. So the reflection coefficient ranges between plus and -1. It has various phases, so it is very natural to plot the reflection coefficient on a polar plot. Let's first consider how the real and imaginary parts of the reflection coefficient would be plotted. This axis right here would be the real part of the reflection coefficient, and this top part would be the imaginary part of the reflection coefficient. So if I had a real part right here of a half, and I had an imaginary part of a half, my reflection coefficient would be plotted right here. Now I could also convert this to a polar form. We start the phase right here from 0. So here is phase equals 0 on the real axis. Phase equal 90 degrees would be here on the imaginary axis. Phase is 180 degrees on the negative real axis. Phase is 270 degrees on the negative imaginary axis. So the point that I just drew that had a reflection coefficient of 0.5 plus j 0.5 can also be written as this magnitude. So it's going to have a magnitude, and what's that going to be? It will be 0.5 squared plus 0.5 squared square rooted. That's its magnitude, and it's going to have a phase. What's that phase? 45 degrees. So it has a magnitude given here and a phase of 45 degrees. That's how we plot our reflection coefficient. Now let's consider how it would look in polar form. In polar form, remember we said that the maximum magnitude is going to be 1. So I'm going to draw a circle right here that has a radius of 1. And I can plot my reflection coefficient right here if it is 1 at a phase of 0, and I can plot it up here if it is 1 at a phase of 90, over here 1 at a phase of 180, and so on. If it happens to be a half right here with a phase of 45 degrees as my previous example, there's a location I would plot my reflection coefficient.